morphology, but more for quantitative Doppler of the hemodynamic and functional severity of valve regurgitation. Angiography and catheterization are no longer necessary or even indicated in the vast majority of cases. In fact, if you look at the prerequisite left ventricular function, the assessment of ejection fraction is an important prerequisite to determine outcome. Ejection fraction has a direct relationship to outcome. If it's reduced even to a normal range, you find an unacceptable long-term survival. Thus, you must identify severity before LV dysfunction, as exemplified by ejection fraction. Next, ventricular volume. It's more consistent with the aspect of chronicity of the problem. Thus, volume per se is not an indicator of severity, such as a dilated cardiomyopathy with regurgitation, which is more severe, regurgitation or the myopathic process. Lastly, diastolic function, which will be illustrated later in this session, does have an indicator of early ventricular dysfunction, can help you make decisions regarding prognosis, but again, is often, once they're present, a little bit too late in the process. Now, if we look at our techniques, color flow Doppler and echocardiography, this is an apex down view of the left ventricle, and we're all familiar with the color flow features of mitral regurgitation as exemplified here. The distribution of velocities in the left atrium are notoriously qualitative, and you can have gross under or overestimate of the magnitude of severity, and this is highlighted by another patient, same projection, apex down, four-chamber view, but an eccentric jet of regurgitation. We all know that we can have gross underestimation of severity when the jet laminates against the wall of the cardiac chamber, in this case left atrium. But let's sort of talk our way through this. I've illustrated a peristernal long axis view of the heart. We often look either from peristernal or apical views or various projections of the heart. In a qualitative sense, look at the distribution of flows into the left atrium. And we often use a grading system, 1, 2, 3, 4. And if you look at the left atrium, with grade 1, it's a mild regurgitation left atrium. And notice, not only does the regurgitant area increase, but the orifice of the regurgitant valve increases with increasing gradations of severity. And this system of grading 1, 2, 3, 4 is extremely qualitative, but also has an extreme trap of being inaccurate. And I'll explain that in a moment. We know that if the jet is central, that we can see the distribution of these velocities very well. But this is plagued by systematic overestimate of severity. We've shown this now time and time again, that if you have jets that occupy a major part of the left atrium, you in fact will systematically overassess the severity of regurgitation. Conversely, if you have an eccentric jet, as shown here, because the jet is laminated against the wall, you will tend to systematically underestimate severity. So if you have a patient who has either an eccentric jet or has a large distribution of contrast in the left atrium, you should use quantitative techniques. And this is where this part of the discussion will go. What makes up quantitative assessment? Well, first of all, it's not two-dimensional. We need to look at the three-dimensional solution. And here you see a balloon sitting in the left atrium representing the volume of regurgitation. But that volume is made up of two components, two essential components. One is the orifice through which the volume is regurgitating, much like aortic stenosis. What's the orifice area? And secondly, what is the volume of blood regurgitating back into a chamber, whether it's aortic regurgitation or mitral? And it's a three-dimensional problem. It's not simply a tomographic view of eccentric or central jet. So we're going to try to calculate orifice area and volume as a means of expressing severity. So I'm going to tell you the answer before telling you how to do it. We have looked at the qualitative exam and related it to our quantitative assessment. Now this is in your handout, so I'm not going to go through each section, but by the time you get to moderately severe or severe regurgitation, the regurgitant volume is at least 50 to 55 cc's of blood, whether aortic or mitral regurgitation. We're going to talk mainly about mitral regurgitation for these examples. And the regurgitant orifice, once you reach moderately severe to severe, is going to be around 30 to 35 millimeters squared. So you have a large orifice as well as a large volume, and you kind of have the idea of what the ranges are, and you're probably unfamiliar with these numbers. But let's go through it. Like all other echo Doppler techniques, this is extremely forgiving. There are at least 3 techniques that can be used to quantitate orifice and volume. One is called PISA, very popular term these days, proximal isovolumic surface area. This is a continuity equation. The second is, in fact, quantitative Doppler. This is everything that Dr. Freeman and Dr. Gurus discussed this morning, the volume across a heart valve. The third technique is volumetric echo and flow. That is, you can measure the volume of a ventricle by planimetry using Simpson's rule and so on, and look at various volumetric exchanges. So PISA, quantitative Doppler, and volumetric techniques. Let's talk about PISA. This is the first technique. When blood goes across a valve, an incompetent valve, in this case, mitral regurgitation, the velocities are converge on that orifice, producing an acceleration pattern. In fact, it looks like a mushroom. That is, the velocity is converging on the orifice, and then those accelerated across the orifice, so it has the stem of the mushroom. Now let's look at this 3-dimensional problem. That is, you have a mushroom, and you have all the features of the continuity equation: proximal flow and distal flow, conservation of mass. What you want to do is calculate the proximal flow and calculate the distal flow. So let's take each component of this equation. How do you determine the area of a hemisphere? It's 2 pi r squared. So you measure the radius of a colored Doppler hemisphere and calculate its area, which is 2 pi r squared. We also can look at the echo machine, and the velocities of that hemisphere, the outer shell, can be determined, and that's v, or velocity, which actually equals proximal flow. Now we want to look at distal flow, the other half of the continuity equation. Area is the unknown. We want to calculate the effective regurgitant orifice. We can get the velocity by taking continuous wave Doppler and looking at the mitral regurgitant velocity. So we have the velocity. Now conservation of mass says flow equals flow across this parallel system. So we simply rearrange the equation to make it equal to one another. Now if we want to calculate the effective regurgitant orifice, we just do a simple algebraic rearrangement of this equation and move the velocity of mitral regurgitation below the proximal flow. And we can calculate effective regurgitant orifice. Very simple algebraic problem. And back to our list, lo and behold, we have these ranges of 30 to 35 millimeters squared as a big orifice, severe regurgitation. If we look at the stroke distance, that's the TVI of mitral regurgitation, remember that equals distance, or how far the blood went, and multiply it times the ERO, we get stroke volume, or regurgitant volume. And remember, the magic number is around 50 to 55 cc's as severe regurgitation. Let's go to the next technique. The pattern that you see on the screen is basically identical to what Dr. Guru was showing, Dr. Freeman was showing. It's the area or volume of a cylinder. If you know area and you know the distance, that's the volume of a cylinder. Let's apply that to mitral regurgitation. If we know the area of the mitral annulus and the TVI, or stroke distance, we can calculate mitral flow. That represents regurgitant volume as well as systemic volume. Then we take Dr. Guru's solution for cardiac output. We take the diameter of the left ventricular outflow tract and the TVI, and we have systemic flow. Now in a patient with regurgitation, we set up a simple algebraic rearrangement. So flow across the mitral valve, which represents both regurgitation as well as forward flow, subtract cardiac output, just subtract those numbers, and you get regurgitant volume. Now let's go back to the normal, to that chart again. Regurgitant volume, 55 cc's is severe. Now we divide this time by the mitral regurgitant TVI, or stroke distance, and we would calculate effective regurgitant orifice. Again, 30 to 35 millimeters squared. So that's technique number 2. We've calculated orifice and volume again. Let's go to the third technique. Commonly, either from 4-chamber view or whatever, we can measure the volume of the ventricle, usually by the Simpson's rule, but we can calculate stroke volume by looking at diastole and systole. The stroke volume of the ventricle sends blood in regurgitation of the mitral valve into the left atrium and out the aortic valve. So we take Dr. Gura's technique, calculate cardiac output across the aortic valve, which we assume is not regurgitant, and we subtract the two, and that would equal regurgitant volume. So this technique is a volumetric technique with flow, and we have regurgitant volume again. Go back to that chart. There it is. 50 to 55 cc's is a large regurgitant volume. We divide that by stroke distance, which is the TVI of the mitral regurgitant jet, and we would get regurgitant orifice. Again, the same number. So we have three well-used, well-proven techniques. Note that this cannot be done very easily at catheterization. So this has changed our clinical practice. We do it on virtually all patients who have the following: eccentric jets, or to a large area of the left atrium covered, because we'll tend to overestimate the degree of regurgitation. What's the role of transesophageal echo? Well, in this example, it's great for looking at the valve for its morphologic characteristics, a prolapsing valve and flail chordae. And its role is really three. One, it's great for structural characterization of a regurgitant valve, both aortic or mitral. It's not very good for quantitation. In fact, I would say that for quantitation, surface echo is the technique of choice, not transesophageal. For qualitative assessment of regurgitation, particularly mitral, it's very good. But remember the limitations of qualitative assessment. Very limited. Lastly, intraoperative assessment of transesophageal is the procedure of choice because, in fact, today, correction of the problem is paramount. With this introduction, I've shown you a whole new era of echocardiography. It's replacing our qualitative techniques, and we've now gone to quantitative assessment of regurgitation. Hopefully we'll have more questions and answers. Thank you. Jamil.
Thank you, Jim.
While echocardiography offers many diagnostic and clinical benefits,